And welcome, and in this video we are going to be talking about arithmetic and geometric sequences, okay? But first things first, what is a sequence? Well, these are sequences. A sequence is just an ordered collection of numbers or algebraic expressions, and there's going to be some sort of pattern associated with the sequence, okay? You may have heard of a very famous sequence called the Fibonacci sequence, okay? What we're going to be talking about in this video is arithmetic and geometric sequences, which are two of the most common types of sequences. Now, before we get into talking about which one is arithmetic, which one is geometric, what is the pattern for each, I want to quickly talk about terms. Terms are what the sequence is made of. The 5 here would be considered the first term of the sequence. The 13 would be the third term. The 21 would be the fifth term. The 24 would be the fourth term in this sequence. And notice that both of these end with like little dots on the end. That is telling us that these sequences actually continue forever. Not all sequences do. Now, when we start talking about sequences, we actually introduce subscript notation, and that allows us to pinpoint and talk about a specific term in the sequence. And this is what I mean by subscript notation. I can see that we have like a lowercase a and then like a 1 underneath it is equal to 5. What that represents, what this is telling us, is that the first term is equal to 5. The second term is equal to 9. The third term is equal to 13. We generally use a lowercase a to talk about the sequence, and then this little number here is what we call the term number, and whatever it's equal to is the value of the term. So notice here, the first term, because the subscript here is 1, is equal to 5. That was the actual value of the term. Over here, I see a sub 3. That's how we pronounce it. A sub 3 is equal to 12. Well, 3 is the term number because we're talking about the third term, and the third term is 12. Now, that is how we identify a specific term and we write it out. We are going to be using subscript notation a lot here. Now, the next thing I want to talk about is, well, which one's arithmetic and which one's geometric? And in order to do that, we have to talk about the pattern for each sequence. If I'm looking at this first sequence right here, notice to get from the first to the second term, we added 4. And to get to the second and third term, we added 4. And that just continued forever and ever, and it would continue forever. We would just continue to add 4 over and over and over again. Now, when a sequence is adding or subtracting the same number over and over and over again, that's what we call an arithmetic sequence. And an arithmetic sequence has what's called a common difference, and that is the value it is increasing or decreasing by between each term. So this common difference would actually be a positive 4. Just know it could also be negative. If the sequence is decreasing, if it was like 10, then 9, then 8, then 7, it's going down by 1 each time, so the common difference would be negative 1. That would still be an arithmetic sequence. In the second example over here, it's not actually adding or subtracting the same number over and over and over again. If you notice, we went from 3 to 6, 6 to 12, 12 to 24, 24 to 48. So it's actually doubling every single time, which you can think about as multiplying by 2. So notice to get from 3 to 6, we multiplied by 2. To get from 6 to 12, we multiplied by 2. To get from 12 to 24, we multiplied by 2, and so on, and so on, and so on. Now, what this is called is a geometric sequence. And a geometric sequence doesn't have a common difference. A common difference is strictly with arithmetic, and it, remember, was the value it was increasing or decreasing by every single time. You can think about it as linear because arithmetic sequences are actually linear in nature. They have a slope. You can think about it like that. Geometric sequences are multiplying every single time or dividing. You can think about it the same way. Multiplying by 1/2 is the same as dividing by 2. So if you are multiplying by some number every single time or dividing by some number every single time, that is going to tell you you have a geometric sequence. And the value you are multiplying by is what's known as the common ratio. Now, if I wanted to, I can continue to find more and more terms for each of these particular sequences. For this arithmetic one over here, we ended with the fifth term, but notice it's just going up by 4 every single time. We're just adding 4. So I can quickly determine that the sixth term would end up being 25. I can determine that the seventh term would then be 29. So notice that I'm just adding over and over and over again, and in order to do that, I need to know the previous term. In order to find the 6th term, I need to know the value of the 5th term. In order to find the value of the 7th term, I need to know the value of the 6th term. Well, what we're doing is actually using what's known as the recursive formula. Okay, and a recursive formula is something that we actually kind of do in our heads, but it's actually important to be able to write it out as well, because computers actually can't, and computers do use recursion. It's a very, very powerful programming tool that is used in a lot of different applications, and we kind of have to program it that way. So the recursion formula is actually pretty straightforward. Okay, now for an arithmetic sequence, we have to state to find the nth term. So you're always going to kind of see this a sub n. That is our way of saying, hey, to find some random term, to find the nth term. Well, to find the 6th term, we needed to know the value of the 5th term, which was the previous one. So we show that by a sub n minus 1. Because if we're finding the nth term, we need to find the previous term. And all we did is we added the common difference. And the common difference is shown by the variable d. Okay? So this is the generic recursion formula, the recursive formula, excuse me. Now, for our sequence, it would actually be a sub n is equal to a sub n minus 1, and then we actually know what the common difference is. It's 4, so I would just write plus 4. And that would actually be half of the recursive formula. The only other thing we need to do is actually state where the sequence started. This tells us how to find the next term, but it doesn't tell us where it started. So for writing the recursive formula, we also need to state what the first term is, and in this case, the first term was 5. So this would end up being the recursive formula for this sequence. Now, over here, we could use the exact same logic. We can find the 6th term. Notice that we were just multiplying by 2 each time. So in order to find what the 4th term was, we had to take the 3rd term, multiply it by 2. To find the 5th term, we had to take the 4th term, multiply it by 2. To find the 6th term, I would need to take the 5th term and multiply it by 2 to get 96. So notice we're still using the exact same idea. The only difference is that we're actually multiplying by the common ratio and not adding by a common difference, because a geometric sequence has a common ratio. An arithmetic sequence has a common difference. So the formula is actually going to look very similar. It's going to be a sub n. Ooh, let me change colors here. It's going to be a sub n is equal to a sub n minus 1. Remember, we're just finding the previous term, and we're multiplying by r, our common ratio. Now, for this sequence, we actually know what that is. This is the generic recursive formula. We need to write it for our specific sequence. Well, that would end up being a sub n is equal to a sub n minus 1 times 2, because our common ratio is 2. And once again, we actually need to state what the first term was to say where this sequence started, and it started at 3. So this would end up being the recursive formula for this particular sequence. Now that's great and everything, except sometimes we don't want to find just the next term. We want to find maybe like 100 terms after that. Maybe I want to know what the 126th term is. Well, it'll be really annoying to constantly just add or multiply over and over and over and over again to find that specific term. But there is a pattern that's emerging here. In order to find the 5th term, we could think about it as taking the first term and adding 4 times. To find the 6th term, we can think about it as taking the first term and adding 4 5 times, and so on and so on and so on. And what this gets us to is something called the explicit formula. The explicit formula is used to pinpoint and find any sequence or any term in the sequence. Okay? Now the recursive formula only helps you find the very next term. The explicit formula helps you find any term. So these are extremely useful. Now for the arithmetic sequence, it's similar. A sub n is equal to, and remember, we needed the first term to write the recursive formula. We also need the first term to write the explicit formula. So a sub n is equal to a sub 1, which is the first term, plus n minus 1 times d. Now, Don't ask me why, for some reason, they have the D over here and not over here. I never particularly actually write it like that. I'm fine taking it either way. Just know that you're probably going to see it written this way. So notice we need to know what the common difference is and what the first term is for the explicit formula and the recursive formula. So now, if I was to write what the explicit formula for this particular sequence would be, well, that would be a sub n is equal to, well, the first term is 5 plus n minus 1 times d. Well, d was 4. So this would end up being the explicit formula. Now, the explicit formula for our geometric sequences is actually very similar. Notice that in order to find the third term, that could be thought of as taking the first term and multiplying it by 2 twice. To find the fifth term, we can think about it as taking the first term and multiplying by 2 4 times, and so on and so on and so on. It's always one less than the term we're actually trying to find. So to find any term in a sequence, we can use the explicit formula, which would be a sub n is equal to the first term, which is a sub 1, times r to the n minus 1 power. So this is the explicit formula. So for our particular sequence up here, that would be written as a sub n is equal to the first term, which is 3, times our common ratio, which is 2, to the n minus 1 power. And there's our formulas, okay? Definitely make sure that you know how to write the formulas for each of these, and especially how to use the explicit formula. Now, I said we can use the explicit formula to find any term in the sequence. So let's take a look at one. For example, let's say I wanted to find the 71st term of this sequence up here. Well, that could actually be very challenging if I just had to continue to add over and over and over again. However, it's actually not hard at all if I know the explicit formula. I can just go ahead and use my explicit formula. Well, I want to find the 71st term, so I'm going to have a sub 71 is equal to, well, our first term, which is 5 plus n minus 1. Now, n is actually, remember, the term number that you're trying to find. Well, in this case, we're trying to find a 71st term, so n would be 71. So 71 minus 1 times our common difference, which would be 4. Now, me personally, I always actually write this like this, because that actually kind of mimics distributive property a little bit more clearly. And just so you know, you can actually plug this into your calculator exactly like so. We're going to be doing 5 plus 4 times 71 minus 1. You can break this down and do it step by step if you want. That's going to be 5 plus 4 times, well, 71 minus 1 would be 70. Well, 4 times 70 would be 280, so this is going to get me 285. So that tells me that the 71st term would be 285. Now, you could use the recursive formula and just keep track and add over and over and over again. However, it's going to be a lot quicker and less complicated and convoluted if you just use the explicit formula. Now let's do the same thing for the geometric sequence. Let's say I wanted to find the 18th term of the geometric sequence. Well, once again, I can just continue to multiply by 2 over and over and over again. However, it's a lot easier if I use my explicit formula. So remember, that would be a sub, well, in this case, we're trying to find the 18th term, so that would be a sub 18 is equal to 3, which is our first term, times 2, which is the common ratio, raised to the n minus 1 power. Well, if I'm trying to find the 18th term, that's going to be the 18 minus 1 power. And 2, that's going to become 2 to the 17th power, which is some pretty big number. That's going to end up becoming 131,072. That's 2 to the 17th, because that'll be 18 minus 1 as the exponent. And then I would finally actually multiply this out. I'm running out of room here, excuse me. We can multiply that by 3 to get 393,216. My apologies for the sloppy handwriting there. Now that is arithmetic and geometric sequences in a nutshell. I'll be releasing another video with just some extra examples using the explicit formula and writing the recursive and explicit formulas for each. But honestly, that's it. It just takes a lot of practice. Make sure that you have those explicit and recursive formulas written down. Make sure you're able to find what the recursive and explicit formula is for each. And definitely make sure you're practicing using the explicit formula. If there's any questions, please feel free to let me know. Otherwise, I look forward to seeing you guys in the next video.